times. That's what he's mentioning here. And it's always good to have a little bit of history before we get into the numbers. So the first the first example that we have that ancient people were also interested in prime numbers is this Ishango bone, which was found in somewhere in mountain of Central Africa around 1960. And it's 6000 BC, remember. And if you look at these two bones, and the bones has a lot of notches, as you can see into that thing. And if you look at the row B of this bone, then you can see those 4 consecutive primes, the notches are there, like 11, 13, 17, and 19. It's not very clear what it means, but at least from here we know that there was some use of these numbers that they were taking off. So there is a curious natural phenomena also, which I want to put in front of you. There is an insect called cicadas, and these insects follow a evolution pattern strategy. What they do, they usually stay underground most of their life, in fact, and they come out from the burrows. They emerge from the burrows only after 13 or 17 years. 13 and 17 years, they come out from there and they fly up. They met, and then the offsprings come out from there, and they survive at the most 1 week. They die after that. So the logic behind this is believed to be that since their evolution cycle, their coming out of the cycle is 13 and 17, so it's prime numbers. So there's very little chance that they will meet the predators. Predators means who will eat them up. They evolve, like what you are seeing now. This coronavirus is going on in. What happened? No, somebody has started sharing screen, and then, hello?
Share the screen, sir.
Yeah, somebody started. You cannot start sharing because somebody else is sharing. You see, that's what coming. You see, somebody else is sharing the screen. Please don't share screen. Then this screen will go away. Brindaban B has started sharing screen. So I request you to kindly come out from sharing. Sure. Let me try once more. Host disabled attendee screening. Okay, so now you have to again allow me.
Sir,
So let me try again.
What's the problem, sir?
Somebody else started sharing. So you know what happened, that my screen is gone now. So
okay, let me check it, sir. Okay, sir, let me check it, sir.
Brindaban B, that's what is coming.
Now you share, sir. Again you share, sir. Now.
Host disabled attendee sharing. That's what it is coming. So kindly allow me once more. No, still not. No, you have to allow me. It said that it is disabled. I can't share. Hello, ma'am. Can you allow me to
try now, sir?
Okay. Yeah, it's fine now. Thank you. Yeah, so I request the participants really please take care so that in between this kind of thing doesn't come. So as you see, as I was telling you, that supposing they come out in the year 12, let's say, so there will be this divisors of 12 like 2, 3, 4, 6, and 12. So the predators who will arrive during this years, they will certainly meet these Magicisadas, and they will most likely will eat them up. Okay, so what happened? Oh, now it is not going. The slide is not moving. Hello? There is some problem. Excuse me.
Sir.
Yeah, the slide is not going down. It's just objecting.
I'll check, sir.
Yeah, it's not coming down. I mean, this clicking thing is not working. Yeah, no. Should I stop share and come again?
Sir, try that, sir. Okay, sir.
Yeah, because it's not going. You see, it's not coming down. It's fixed.
Share again, sir.
Okay, so I'll stop sharing and I share again. It's not coming. Somehow it's not coming. Share screen. Click here. Share. Yeah, it's not coming. Something is stuck. Oh, it's not moving. Mm. No, it's not moving, ma'am.
Hello, sir.
It's not moving. The slide is not coming down. It is just fixed.
Sir, please, sir, you can mail your PPT to the organizers. Sir,
Yes.
you can mail your PPT to organizers, then they'll present. Then they can present, sir.
Is it?
Hello, excuse me, sir. If you mail your PPT to the organizers,
Yeah, I'm just mailing.
then they can present well.
I'm just trying to see if once more if it works. Just I'm just trying to share once more. No,
Yes.
it's not working.
Sir, you send your PPT.
So I send by Gmail.
Okay.
So I'm just hello.
Hello.
देखता हूँ मैं. Okay. So I'm just, ma'am, trying once to close my PPT and just sharing once more. If it works. Just trying once more. Just give me a little bit. It's not, it's working now. So yeah, is it okay now? Can one see the slides?
Yes,
Yeah,
sir.
okay.
We can see, sir.
Okay, okay. So sorry for the interruption. I think that was a good suggestion to close it down. Okay, so let's move from here. And this advantage what I was talking about is enough to use prime numbers in the life cycle of these insects. So a prime number first. And as you can see, a prime number is a natural number, which has to be bigger than 1. So question of whether 1 is prime or not doesn't come here. And as you know that it has only itself and 1 is the divisor. So remember that it's a natural number and it has bigger than 1. And fundamental theorem, as I was talking about, it talks about that every positive integer can be written as a product of powers of primes, if it is a composite number, and if it is a prime, it's already a prime. But the interesting part here, as you see, that it is unique up to order. So it's unique up to order is what helps us to move the economy and everything. If you have more than one factorization of same number, then life could be very difficult. So that's what I'll come back to again later. So let me look at a little bit of mathematics of Ramanujan before I move into again there. So people know about this 1729, this taxi cab problem. And all of you know the story that, immediately he was almost in his deathbed, but he could tell Hardy that this number is the smallest number, which could be written as a sum of cubes of two different ways. Sum of cubes of two integers in two different ways. This is the smallest integer. And so that was the brilliance of him, that even when he was at the end of his life, still he could think about numbers and playing around them. Let's look at this expression phi x, which is 1 minus x to the power n equals to 1 to infinity. I take the product, this is a formal product. And if you expand it, it will be like 1 minus x, x2, x5. It will, it goes on like that one. And it was Euler first. So you have a product expansion, and then Euler got a sum from the product. It's, you see, and you can see there's 3n square minus n to the power n by 2. Those are called pentagonal numbers, and they come up there when you write this phi x as a sum, as an infinite sum. And what happened? Gauss studied this third power of this one. So this was Euler, and then Gauss studied the third power this of 1 minus x to the power n. And so there is a x missing there, x to the power n square plus n over 2 will be there. So n square plus n over 2, they are called triangular numbers. So you see, people have studied these numbers, and this phi x plays an important role in studying all these numbers that you are seeing here. And what Ramanujan did, he studied the 24th power of this expression, that is 1 minus x to the power n to the power 24. And you can see that it like the first one is 1, the coefficients I'm talking about, this is 24 minus 24 to 52. And then he could get some expression, which is tau n, q to the power n minus 1. It comes out like that one. And the conjecture is that tau n is never 0. As you see from here, that is still a conjecture. And we know many values, but still this tau function is not very well understood. And he studied, in fact, this function, and this goes by his name. These tau functions are called Ramanujan tau function. And he studied these things. As you can see, this tau 6 is tau 2 into the tau 3. Put in there, you can see that. So this is a nice pattern is there. They're called multiplicative functions. Take two integers, which are co-prime. Then, in fact, tau mn, if you want to find out, if you know the value of tau m and tau n, you can get the value of tau mn. So he conjectured that one, that it is multiplicative. And then he got an expression of powers of primes. That is tau p power n is tau p to the power n minus 1. So it goes on like that one. And you can check that, small calculation is there, that tau 2 square p equal to 2n equal to 2. It's exactly tau 2 minus 2 to the power 11. It's minus 1.1472, as you can see, tau 4 from that above expression. So these were his conjectures. And it was later proven by Pierre Delin, who got Fields Medal. So these expressions are just not this kind of innocuous expression. So they are what is called modular forms. People in the audience who know about modular forms, they can easily recognize that it's a very important function. And Ramanujan had this in linking that, you know, they will play a very vital role. And modular forms really played a Am I audible now? Hello?
Yes, sir. Yes, sir.
Yeah, and somehow something is happening. You know, I got muted and then I had to unmute again. Oh, now it is again gone. You know, if you do something in the between, then this file doesn't move. It's again the same problem. I have to again go and start from the beginning. No, it doesn't work. So if you do anything in between, no, somehow I'm trying to present from my home and it doesn't work. This file has got stuck now. Stop share. Just doesn't work.
நான் பேசக்கூடாது பண்ணக்கூடாது ஏதாவது பண்ணி ஒரு இடத்துல ஒரு ஆளுக்கு நிம்மதியா இருந்தா பரவாயில்ல. எதுக்கு நிம்மதியில பண்ணி வச்சங்காட்டி எனக்கு இருக்குது. ஒருத்தர் இது பண்ணக்கூடாது, நான் இங்கேயும் போகக்கூடாது, இங்கேயும் விடுறது கிடையாது.
Excuse me. Hello?
Yes, sir.
Yeah, what I'm asking now, I'm already there. Please don't do anything in between because I have to go to the Gmail. Please don't mute or unmute anything. Ask or yeah, because now it is there. Please don't, because the thing is that it is getting stuck in between if you do something. Okay, so now it is okay. Just I request everybody, if you do something, then I have to really stop today and maybe try some other day, because it's becoming difficult to go back again and try to present. So just sit in there, listen, whatever questions or whatever is there, we can talk later. Okay. So is it fine now, ma'am? Hello?
Okay, sir. Okay, sir. Okay, you are
Okay,
fine. You're
okay.
fine. You are audible.
Yeah, so that's what was conjectured, and it was proved by Pierre Delling, who got Fields Medal for proving this kind. This is true for other coefficients of what's called modular form. That's the Fourier expansion that you have for weight 12 modular cusp form. In fact, it's called, goes by Ramanujan's name. So he did something more. You know, you look at this sigma 11n, which is again an arithmetic function. Is the 11th power of divisors of n. Like if you take sigma 11 2. 1 and 2 divide, so 1 to the power 11 plus 2 to the power 11 is 2049. So what he proved is startling identification that sigma 11n in fact is same as tau n in mod 61, mod 691. So for you take any natural number n, the sigma 11n minus tau n will be always divisible by 691. So you proved that one, and you can check that. Suppose you take 2, n equals to 2, sigma 11 2 minus tau 2, it's like 691 into 3. So this is some work that I was trying to say, and little more about Ramanujan's work. That in 1919 in Indian Journal of Mathematics, Ramanujan published this a new proof of what is called Bertrand's postulate. So what is Bertrand's postulate? I'll come back later again on that one. That if you take n, any integer bigger than, strictly bigger than 1, then between n and 2n, you can take n equals to 3, 2n is 6. So between 3 and 6, at least one prime will be there. So that's what Bertrand's postulate. It is postulate. It was later proved, and I'll come back to that one. So what Ramanujan did, so that means this, if you look at this pi x is the pi function, which is the number of primes up to x, is a prime counting function. So saying that there is one prime between n and 2n is same as showing that pi x minus pi x over 2 is always bigger than equal to 1. But what Ramanujan did, it's, if you take a number, take the twice the number, more than one primes are there. So in fact, he got a better bound. What he proved that pi x minus pi x over 2 is bigger than equal to 1 for x bigger than equal to 2, bigger than equal to 2 if you take bigger than equal to 11 numbers from there. So it goes on like that. It goes on like that. That was his proof. And if you look at the converse question, that suppose, so that is what is called nth Ramanujan prime. So nth Ramanujan prime is the least integer Rn, for which pi x minus pi x over 2 is bigger than equal to n. Okay, so the converse one. So as you can see, 2, 11, 7, 10, 29, 41, these are the first 5 Ramanujan primes. And they're all prime numbers, in fact. And it's like 2n. Suppose you look at the first Ramanujan prime, then it is like the second. Is it okay? Is there any problem? Okay, so it's like P2n. Suppose you want to find out the 5th Ramanujan prime, it's like almost like the 10th usual prime. So Rn is like P2n. I'll come back later into that one. So let's look at primes a little more. That, what I'm saying, that we are fortunate to have primes. Remember that in the definition of prime, we're saying it's a natural number. So remove natural number, make it rational number. Suppose in the definition you put a rational number, then you have no prime at all. Because if suppose 2, then half divides 2, you see. So similarly 3, then 1/3 divides 3. So if you take a rational number, then there is no prime that we have. And what about unique factorization, which I was putting in a red line, that unique factorization is very important. Because you look at this example, z square root of minus 5. So you have just attached, you have z, and you have just taken this square root of minus 5. You have expanded the ring z into z square root of minus 5. So they look like a plus b square root of minus 5, the numbers in z square root of minus 5. And as you can see, so z square root of minus 5 includes z. Okay, so it's inside. So as you can see, 6, we know 6 is 2 into, and you can see that there is one more factorization of 6, that is 1 plus square root of minus 5 and 1 minus square root of minus 5. And one can prove that they are in fact primes. Yeah, there's some disturbances are always coming. So 6 is, so you have 6. In Z, you have 6 as 2 into 3, only one factorization that you have. But if you just go beyond Z, then it is not assured that you have just one factorization. Again, there is a failure, which I was talking about. So this is a failure of unique factorization. As you can see in Z square root of minus 5, it fails. So there is a group, I'm not going detail into that one. So the group which measures this failure. So, you know, in the ring, we have ideals. So you take the ideals and go quotient modulo this principal ideals, which is generated by a single element. And then that forms a group. That is what is CK. It's called a class group. And in fact, it's a big result in algebraic number theory that it's a finite abelian group. So it's finite. So in Z, what great thing happens in Z that you have unique factorization there? Because every ideal in Z is a principal ideal. It's generated by a single element. So you go quotienting that and try to find out how many ideals are there which are not generated by a single element and count them. So this result tells you that there are only finitely many such ideals will be there, which is not generated linearly independent, which is not generated by a single element. More than one element they will be generated. So like that example what I gave you, that Z square root of minus 5. In fact, you have rational numbers field Q, you have Z, you have Q square root of minus 5, and then you have Z square root of minus 5. So Z square root of minus 5, there are only 2 ideals you will find, which is linearly independent and which is generated by more than one element. So this is an area that I am interested in. My research goes on, one part of my research goes on in trying to measure this failure. Okay, a little bit. So GCD, all of us know, not going into the definition. So as I told you that my lecture will be very, very simple. And if you sit down, you can look into the things. I'll try to point out something interesting every time I come into some problem. So how do we calculate GCD? 2261, 1275. We all know this is what is called Euclid's algorithm. And divide the bigger number by the smaller number, collect the residue. And then it's a small exercise to show that the residue of the GCD of 2261, 1275 is same as if you take the smaller number and the residue after dividing. Keep on doing that. And then finally, you will end with the residue, with the GCD. And in fact, this is by Euclid. And still, this is the best algorithm that we have. If you know a little bit of cryptography and some protocols in crypto, everywhere this GCD has been calculated. And the computer will be following this algorithm of Euclid. Even now, this is the best one. So we are talking about integer factorization. We have an integer and we want to find out what are the prime numbers that it is built up of. So this is what is called the integer factorization. And fortunately or unfortunately, whatever you call it, we don't have a polynomial time algorithm right now that I give you a big number, composite number, and even it is made up of 2 primes, let's say. And then I tell you that, can you tell me the primes, at least one prime? It's a difficult problem. So we don't have till now a polynomial time, what is called quickly. Quickly means, you know, you have whatever computer strength you have, you put it into that one, and this is difficult problem. We don't have a algorithm right now. And as I'm just putting in a few comments there, that there is no particular reason that why you don't have a polynomial time algorithm. I mean, we say it's a hard problem, but there's no reason that why it is a hard problem. Okay, so there are quantum computers claim there is so-called source algorithm, but quantum computers are still some time off from now. And this difficulty helps us in our information security. Whatever the informations that we are sending, our credit card and, you know, email, our mobile and all other things, one of the main difficulty is this factorization. And the whole industry is depending on that. So what is called RSA, the most popular public key crypto system, is based on this difficulty. Once this difficulty is gone, then this system has to be changed. Okay, so this is an interesting problem, difficult problem. And the next thing that I come is, are there infinitely many primes? Of course, all of you know. And the next, even better question is that, can you get a estimate of how many primes are there up to, let's say, a very, very huge number. So these are the questions that interest us. As I was telling you, that primes are not very well distributed. Yes, there are infinitely many primes, but it's not obvious. We have Z. So Z is, I'm trying to put in front of you, Z is so interesting, so helpful, so nice ring. So you consider this simple ring, A over B, and make B is co-prime to 30. You have just 3 primes. Just 3 primes. So infinitely many primes is a luxury that we have. And I include a proof of Euclid, which I like the proof that there are infinitely many primes. All of you may know it, but it's a beautiful proof. I just can't resist myself presenting this proof here. So what Euclid does, it's a existential proof. So what Euclid does, let's say we have finitely many primes, P1, P2 up to Pn. What he does, he takes a product of them, let's say capital P, and then you add 1. Suppose you have finitely many primes, just let's say 2, 3, 5, 7, 11, 13, or whatever it is. Take a product of them, add 1, you can produce a new prime. N is certainly not 1. And so by fundamental theorem of arithmetic, some prime has to divide it. Let's say little p divides it. And this p will be different from this p1, p2, pn, what you have there, in fact, bigger than that. So suppose it is not, then it is the same for n and same for p. So that p should divide 1. But we know that no prime divides 1. So that's the contradiction. So every time you say that I have only finitely many primes, by this method, you can prove that there is a new one next to that. So there are many proofs, like in mathematics, we have such a fundamental result that there are infinitely many primes. Euclid's proof is the first one. And many, many people have given a lot of other proofs like Goldbach, Euler, Dirichlet, Erdos, it goes on. And every time you have a new proof of these primes numbers that there are infinitely many, we get to know some new properties of these prime numbers. One of my students who is a faculty at IIT Indore now is Vivekananda Majhi. During his project period when he was doing it, he gave another proof of infinitude of primes. That's 2015. So goes on, and of course there are infinitely many composite numbers because primes are there. And how about largest prime? Look at this number. It's discovered recently. I'll come back to that one. This is a particular type of prime, and it has 2 million decimal places. Okay, so the primes are of quite fashionable, and there are many, many people, they look for larger primes, and Euclid's theorem tells you that, you know, it never ends. So whatever you say that is largest, one should be able to produce, go to the next. And as I told you that in crypto system, these large primes are very, very useful, and our security depends on the, you know, how big that is. So I was talking about Bertrand's postulate. Actually, Bertrand wanted to give another proof of infinitude of primes. That is, there are infinitely many primes. And what you have already seen that there is always at least one prime between n and 2n. How does it get a proof of infinitely many primes? So suppose P is the largest prime. I mean, like Pn, what I was writing there. Suppose P is the largest prime. Then let's take n equals to P plus 1. And look at 2n, that is 2 into P plus 1. The postulate says that between n and 2n, there is at least one prime. So here n is P plus 1 and 2n is 2 into P plus 1. There will be at least one prime, and that will be bigger than that one. So that will contradict the thing that there are only finitely many primes and P is the largest one. So you can always produce a larger than whatever you have produced. So it was proven later by Chebyshev, and of course by Paul Erdos later, and of course Ramanujan gave another proof. In fact, better result that Ramanujan had of this one. Now the question I was telling, how many primes are there up to x? You know, we are infinitely many, but can you get an estimate that I put x equal to some 10 million or, you know, whatever number you can imagine, how many primes you can have there? Okay, so these are simple questions. So how many prime numbers are there up to a big, large number x? So this is the prime counting function. When I was talking about Ramanujan's work, I was talking about this pi function. So pi is simply the cardinality of this set that count all the primes up to x. Count means what is the number? So pi x is the number. So this is a famous result in analytic number theory, which is that pi x is approximately log x. There is some error. So this again, studying this error that pi x minus x over log x, how big that error is another study of in number theory. And like if you take x equals to 10, pi x is 4. We know there are 4 primes up to x. And this estimate gives you 4.3 x over log x. So if you take 100, then we have 25 primes, and this estimate gives you 21.7. So the error keeps creeping up, and in fact, this function Gauss likes what is called Lie function. So this is better. It gives better estimate, 2 up to x, 1 over log t dt. So this is what is prime number theorem, and it was proven first by simultaneously at the same time this Hadamard and de la Vallée-Pougin, and at the same time, that's why the proof goes both the name, we take the name of both of them, that up to x there are x over log x number of primes approximately. So you look at here, so the students were sitting there, you have a very basic question that how many primes are there up to a big number. And here you see they use complex analysis, what is called Riemann zeta function, which is n equals to 1 to infinity n to the power minus s. S is a complex number here. And again, you see there is a sum and there is a product. So always we are interested into this kind of things where there is an identity between a sum and a product. And of course, real S has to be bigger than 1, and then you can continue it to the other side. We have this critical strip, all of us know. And so look at that particular small question, but this Riemann zeta function is being used by both of them. And in fact, we have a very $1 million problem involved here to show that the zeros, the non-trivial, so-called non-trivial zeros, are on the half line. So you have 0, you have 1, you have half here. So on this half line, all the zeros of these functions, non-trivial zeros are there. So that is what is called Riemann hypothesis, which is still not known, the proof. We all expect, people have gone ahead assuming that. So so-called elementary proof, as you have seen that Hadamard and de la Vallée-Pougin used complex analysis to give a proof for prime number theorem. So later an elementary, don't think elementary means simple. It's just that they didn't use complex analysis. Complex number is not used there, and it's by Erdos and Selberg. But it is again much more difficult than the other proof. Okay, so let's go into how to sieving thing. That now you're talking about primes. So I give you a bag full of numbers. Can you give me a method to really sieve out the prime numbers from there? That's the problem. I give you a bag full of numbers. Give me a method to sieve out the prime numbers. So this is again Eratosthenes, the first one. It's a sieve, and this is 3rd century BC, again in Greek. So there's a nice rhyme involved into that Eratosthenes sieve, which is being taught in maybe 8th, 9th standard in these days. So sift the 2s, sift the 3s, the sieve Eratosthenes. When the multiples sublime, the numbers that remain are prime. That keep on removing the multiples, and finally the numbers which survive are prime numbers. That's the sieve. And this is the simplest algorithm, but it is so slow that you cannot use it in modern days. And there is a small animation is there. As you see, I've taken up to 120, and first 2, 3, and keep on removing the multiples. And you can see that the multiples are being removed, and what remains is our prime numbers. So from 2 to 103. Okay, so that's the Eratosthenes sieve. And let's move into a type of prime, what is called SG prime. So this is called Sophie Germain prime. It goes on by the name of Sophie. She wanted to prove what is called Fermat's last theorem. And so she considered, so these primes P, so the 2P plus 1 is also prime. You see, you take a prime, like let's say 3. You take 3 into 2 is 6, 6 plus 1, 7. So 3 is a SG prime, because 2 times 3 plus 1 is also a prime. Like you have the consecutive things 2, 3, 5, 11, they are all SG primes. And the problem involved here is, do there exist infinitely many SG primes? Can anybody prove that yes, this kind of primes where 2 times that particular number plus 1 is also a prime? Look at that, now extra condition has been put. But we don't have a proof of this one, that there exist infinitely many such primes, and why these primes are important, it'll come into the next slide. So what Sophie wanted to prove? Sophie wanted to prove this Fermat's last theorem, that x to the power n plus y to the power n equal to z to the power n has for n bigger than equal to 3, there it has no non-trivial integer solutions. So she was interested in proving that one, and she could not prove for the whole all things, but she could prove it for this kind of primes. At that time, this was a remarkable result, that if you choose this p, x to the power p, that p is a SG prime, then she gave a proof that there do not exist any proof of that. Okay, so now why I was talking about this Sophie Germain prime, because these days it is quite important for information security. This prime is called a safe prime if it is 2 times a Sophie Germain prime plus 1. That means you take a p, so 2p plus 1 is also a prime, that I know if it is a SG prime. So that 2p plus 1 is actually called a safe prime, for example, x 107, because it is 2 into 53 plus 1. And the safe primes are being used, as I was telling you, in an RSA crypto system. We have a composite number n, and which is a product of just 2 primes, p times q. And the integer factorization is a difficult problem that helps us to keep n unbreakable. And the safe primes are used many a times because it is resistant to certain attacks on those crypto systems. So Sophie would not have imagined at that time that the primes that she had in mind is going to contribute the security of our systems in a 21st century. So let's move into another conjecture, what is called Goldbach conjecture. Many people will be aware of that one. The Goldbach wrote a letter to Euler and asked that whether every even integer bigger than 2 was the sum of just 2 primes. Okay, this is the strong form, what is called. So every even integer bigger than 2, is it possible to write it by just a sum of 2 primes? Okay, so weak Goldbach conjecture says that every odd integer n bigger than 5 can be expressed as a sum of 3 primes. This is called weak because the strong one implies the weak, because if n minus 3 is a sum of 2 primes, certainly n is a sum of 3 primes. Okay, so this has the Hardy Littlewood proved this one for sufficiently large odd numbers, assuming what is called another form of Riemann hypothesis. Vinogradov removed that Riemann hypothesis dependence part. And Olivier Ramare proved that every even integer bigger than equal to 4 is a sum of 6 primes. In 2012, Terence Tao made it that is a sum of 5 primes. And then Helpgott in 2013 claimed this weak Goldbach conjecture, and they still yet to be published, that paper. So this is about Goldbach conjecture, and then we don't know about the conjecture, but what we can do that we can make a nice comet out of it. You see, take 4. 4 is 2 plus 2, 6 is 3 plus 3, 8 is 5 plus 3. But as soon as you go to 10, you can see that 10 can be written in 2 different ways as a sum of 2 primes, 3 plus 7, 5 plus 5. Repetition is allowed. Similarly, you go to 100, you can see the number of expressions keep on increasing. So it's quite nice that you take a number and you see how many ways you can write it as a sum of 2 primes. So that's how it gives rise to what is called Goldbach conjecture. You can graph it, in fact. So plot this function GE for all even integers bigger than 2. What is that? Take the number, take that even integer bigger than 2, even integer, you remember, and see the output, that how many different ways you can write it. Okay, so if you plot that one, you can see this nice, beautiful comet that comes out of there. The colors I can tell you. So the coloring pattern is mod 3, I have seen it. So mod 3, there will be either 0, 1, or 2. So if it is 0, if it is 0, then I put red, and blue if it is 1, and it is green for 2. Okay, so this is just EA, but it might give rise to some idea, but people do study this comet also. So next I move into perfect numbers. So a number is called perfect if it is, look at all its divisors. Divisor means I'm talking about 1 as well as the number itself. Then if the sum is twice the number, then we call it a perfect number. And in fact, it was of interest to a colleague of Plato, which is Tarentum, and who claimed that if suppose 2 to the power n minus 1 is a prime number, 2 to the power n minus 1 is a prime number, let's take n equals to 3. So 2 to the power 3 is 8, 8 minus 1 is 7, which is a prime number. Then you add the sum of the first 2 to the power n minus 1 positive integers, then it is a perfect number. People wanted to characterize, and that's what comes up in Euclid's book of elements, that yes, that is true. If 2 to the power n minus 1 is a prime number, then if you count up to that 2 to the power n minus 1 positive integers, then this becomes 2 to the power n minus 1 into 2 to the power n minus 1. You can see the brackets. So then it is perfect number. You put n equals to 2. So 2 to the power 2 is 4 minus 1 is 3 is a prime, and it gives rise to 6 as a perfect number. You can check 6. The divisors is 1, 3, 2, and 6. So it's exactly 12 if you sum them up. And if you take n equals to 3, as I told you that it is again 2 to the power n minus 1 is a prime, and you can put there into this formula 2 to the power exponent n minus 1 into in the bracket 2 to the power n minus 1, it comes out to be 28. But look at that. Why I'm putting this one? Because you see, these are the perfect numbers that was known to the ancient people also. And all of them are even numbers. That's why there cannot exist odd numbers which are perfect. There's no reason. That's what Descartes wrote to Marcin, that why he could not find any reason that why odd perfect numbers cannot exist. And people might be interested who are in the research, what big deal about 2 to the power n minus 1 is a prime? So Fermat studied that one. He took, instead of 2, he took a, some integer a to the power n minus 1. And what he proved, that if it is a prime, then a has to be equal to 2, and n is also a prime. So if a to the power n minus 1 is a prime number, then a has to be 2. There's no other choice. And n has to be a prime number also. Such primes are called Marcin primes. So 2 to the minus 1, these primes are called Marcin primes. And you have seen the largest prime that I had put in, which was discovered in December 2018 by a courier boy, in fact, courier man. And so this is, you can see that the exponent is a prime number also. So it is of the form 2 to the power p minus 1, and it has so many digits. So till now, we know only 51 Marcin primes. And the conjecture is that there exist infinitely many. So look at that, the 51th prime number is already so big. And the conjecture says that there are infinitely many such prime numbers. So you can imagine how sparse they are being distributed. And to prove such a conjecture, you need to have a very big technology, very interesting sieve to really sieve out this kind of particular primes. So not known. So this, the converse of the even perfect number was proved by Euler, again on amicable, it's posthumously, after his death only this was published, that suppose this is a perfect number, 2 to the power n minus 1, then whether that is a prime, 2 to the power n minus 1, yes, that is true. So that's an if and only thing. So to find even perfect numbers, just look for Marcin primes, 2 to the power p minus 1. So Fermat also studied this a to the power n plus 1, don't remember that was minus 1. But he studied this also, and he thought that I don't know, somebody's scribbling. So this n, if it is a prime, a to the power n plus 1, then n has to be of the form 2 to the power r. And these are called 2 to the power r plus 1 are called Fermat numbers. Fermat thought, in fact, that all of them are prime numbers, but only for 0, 1, 2, 3, and 4 for n, that they are prime numbers. Euler proved that the sixth one is in fact composite. So they are called Fermat numbers, and Gauss was also interested in those Fermat numbers. And in fact, he proved something that, what is called that constructed by straight edge and compass. If you take this kind of numbers 2 to the power k into, take those Fermat primes, P1, P2, PR, no more Fermat primes are being discovered except those which I have quoted. Then you can construct a regular n-gon if you consider your n is like of this form. So you can see that n could be of these numbers, 3, 5, 17, 257, etc. And in fact, he wanted a 17-gon polygon to be constructed over his tombstone, but it was not possible. So they could not make it even without using everything. Also, they could not construct that. So this was Fermat numbers. People know about twin primes. So twin primes are the smallest, the gap is smallest between them. That's like, forget about 2, 3, that's on 1. 2 is extraordinary prime, as I was telling you. And any other prime, the smallest gap, we are studying about the gaps between the prime numbers. So the gap is at least 2. And the upper bound goes on that, you know, primes become sparse and sparse as you go there. But what this conjecture says, remarkable thing that, you know, so there are many twin primes like 3, 5, 5, 7, 11, 13, 17, 19, as you see. There are infinitely many such twin primes. So P is a prime number and P plus 2 is also a prime number. So this couple P comma P plus 2, there are infinitely many such pairs. That's what is twin prime conjecture says, that P and P plus 2 is also a prime. So we have infinitely many such prime numbers. And there's a general conjecture also that Y2, increase it, it might become simpler. So what is the status now? The status is that Zhang has proved that this difference can be bounded, is uniformly bounded. So that's called prime number, prime bounded prime gap, that Pn plus 1 minus Pn, the difference is bounded. So that means, you know, he could show that not 2, but to a much bigger number, there are infinitely many such primes there. And Zhang's result was significantly improved by Maynard, who showed that, who used a different sieve. As you see that we have to use like a sieve, like Eratosthenes one, and sieve out this kind of primes from the number system, that we have. And according to my guess, my knowledge, that the thing is that difference is 12. That P and P plus 12, Pn and Pn plus 12. So he could show that there are infinitely many such pairs. But you see, that the twin prime conjecture is still open. That the gap is just 2. It's just 12 it's talking about. So the latest result that we have it with a lot of conditions are there still. It's not easy. And so this twin prime conjecture is still open. Now let me come to what is called congruent numbers. And let me see the time also, 11:09. So people know, so this is a problem that I want to really present in front of you, that a very innocuous, simple looking problem, it could be so deep, so much of mathematics could be involved in such a simple looking problem that we are going to talk about it. So let's look at a right triangle, rational sides, allow rational sides, right angle triangle, you know, like 3, 4, 5 is an example. And you can get infinitely many such, you know, Pythagorean triples that we call it. Just keep on scaling them, like I have scaled it, dividing by 2. So the question is that if you ever take a rational right angle triangle, the area is irrational, that we know. But the converse question that one is interested in, I give you a rational number. Is it possible to find a right rational triangle whose area is that given a rational number? Okay, so that's the question. Like Fermat showed that, you know, if you take 1, the number 1, which is a rational number, you cannot find a rational right angle triangle, rational sides, remember. So rational right angle triangle whose area is 1. In fact, for 2 also you cannot find, for 3 also you cannot find. Okay, so the question is that which rational numbers occur as the area of a rational right angle triangle? Can you give a algorithm? Let's say an algorithm, I give you a rational number, check it whether it's a rational, whether it's a area of a rational right angle triangle or not. So a positive rational number n is called a congruent number if there exists a right angle triangle, rational sides whose area is n. Okay. So if suppose this happens, that I give you a rational integer, a rational number n, and you can get me a, b, c, where a, b, c are 3 sides of a rational right angle triangle whose area is this given n. Then I call n a congruent number. Okay, so we have 2 equations, simultaneous equations has to be satisfied. You have to find ABC such that a square plus b square equal to c square, and half AB is n. For example, if you take n equals to 5, you can see this is a rational right angle triangle. It will give whose area is 5. Take n equals to 7. These 3 rational numbers are going to form a right angle triangle whose area is 7. So 5 is a congruent number, 7 is a congruent number. So what congruent number problem asks is describe all these congruent numbers. How do they look like? Now the thing is that you can do a little bit of scaling, and in fact from rational numbers, you can come to what is called square-free integers. Like suppose 18 over 7 is given to you, you can multiply by 7 over 3 whole square and can make it 14. So 14 is a square-free integer. So focus on the congruent number problem for square-free positive integers, because scaling is allowed, as we have seen. So I give you a square-free positive integer n. Okay, the question is to show that n is a congruent number, find me an integral right angle triangle. Now it is integral because you have come from rational to positive square-free integers. So the integral sides will be there, whose area, the square-free part, is n. Okay, so then if you write m square n, you can find actually the area. So this, you might say that what about, we have these Pythagorean triplets, like k square minus l square, 2kl. All of us know that this is a parametric form of Pythagorean triples. What about that? That might give you all right angle triangles. But the problem is that, I have just done a little bit of calculation by taking k equals to 2, l equals to 1. So up to 9, k plus l is 9, little bit of calculation. And we can go on doing that one to find that the congruent numbers keep coming there, as you can see. But the problem is that I give you a number. So this calculation you can do, you can extend it as big as you wish. But the problem is that given an integer, just I want to put you in the last slide, suppose 53, which is a congruent number. And you want to check that by this algorithm that 53 is a congruent number or not, then you see k, how big the k comes up and l comes up there. So it's not symmetric. It's not very convenient to check this, this algorithm, what you have by Pythagorean triples, to check whether a given integer, a given number is a congruent number or not. Okay, so this algorithm is a bad algorithm that we have it. And you can see that Fibonacci studied it in 10th century, these congruent numbers. And he got another proof of that one is not a congruent number. So let me give you a small proof of, not complete proof. You have to assume something that one, you cannot construct right rational triangle with area 1. Let's say the sides are ABC. Then we need to have this equation from the left hand side. If you see a square plus b square equal to c square, and half of AB is 1. At right side, you consider this polynomial equation, y square equal to x to the power 4 minus 1. Now there is a relationship between the left hand side and the right hand side. You could give a change of variable, and you can go from like x equals to c over 2 and y equals to absolute value of a square minus b square over 4 to go to the curve y square equal to x to the power 4 minus 1. Okay, and if you know x and y, you can construct ABC from there. I'm not saying they're inverse to each other, but you can convert. If there is a positive solution here, if there is a solution in the left hand side, that means if you can find ABC, then satisfying these conditions, then you have a solution xy you can construct. Conversely, if suppose you have a solution, positive rational solution of y square equal to x to the power 4 minus 1, then you can construct ABC from there. Okay. But unfortunately, I mean, the proof is that this equation, this polynomial equation y square equal to x to the power 4 minus 1 has no solution in positive rationals. So we cannot find ABC, which will satisfy that half of AB is 1 and a square plus b square equal to c square. Similarly, similar proof goes on for 2. It's just that you have to take x to the power 4 plus 1 and half of AB is 2. And in both these cases, the positive solution doesn't exist for these equations. So that's a proof which Fermat gave. And to show that there is no positive rational solution, you have to follow what is called descent method to show that there is no positive rational solution. This is a proof, and you can use this proof to give a very strange, weird, I call it, proof that root 2 is irrational. Root 2 is irrational. All of us know that root 2 is irrational. So root 2 is irrational, and I give you a small proof using that one is not a congruent number. So suppose root 2 is rational. If root 2 is rational, then consider this root 2, and 2. They will form a rational right angle triangle whose area is 1. So then 1 will be a congruent number, but we know that 1 is not a congruent number. So root 2 cannot be rational. So root 2 is irrational. Small proof. Okay, ma'am, how long my time will be there?
Sir, take your own time, sir.
I can take?
Take your own time.
Sir, if you can end this, sir. If you
So
want.
you want me to end here?
Yes, sir. You want to take time, sir? More?
No, at least, okay, so I go to the next problem and then I will end. So I am skipping this one. I wanted to present a little bit, but maybe people have different occupations.
Okay, sir.
Okay, so I'll skip through. So please excuse me. I wanted to give a little bit about this congruent number problem, but I have already given some idea. So there is a very close relationship. What is called elliptic curve. So one looks at non-trivial solutions, and if you have non-trivial solution, then you have that n is a congruent number. Anyway, since lack of time, I'm going through fast. Okay, so I'm not going into tunnel's result. Okay, so this is the last problem that I have to present in front of you. I'll take just 3 minutes. So this is called 3n plus 1 problem. So it's a game that, somebody was sitting collage. In fact, it's called collage conjecture. So he was sitting in a boring meeting. Many of you have to face such boring meetings. So he was playing with numbers. So what is this game? This game is that you start with any number that you start positive integer start with. And if it is an even integer, divide it by 2. If it is an odd integer, multiply it by 3 and add 1. Okay, so this is a function that f of n, what do you do? N is given to you. What is the output? That if n is even, then it is n over 2. And if it is odd, multiply by 3 and add 1. Okay, so the conjecture says that you keep on doing this operation. You will reach 1. That's the thing. You will always reach 1. For example, if you take n equals to 6, 6 is even. So divide by 2, 3. And 3 is odd, multiply by 3 plus 1 is 10. Keep on doing it. You see, as soon as the 2 cups or power of 2 cups, you are at 1. So the conjecture says that this process will eventually reach the number 1, regardless of which positive integer is chosen initially. So any big positive integer you can choose, play this game, and then you have to reach 1 at some point. Okay, so this has physical meaning also. Many numbers, I mean, very big numbers up to very big numbers, this has been already checked. For example, if you take n equals to 11, you see you have to do so many steps. Start playing this game and you will reach, as soon as it is 8, as you can see, 2 power something, 16 in fact, then you know you are going to reach 1. Any power of 2 comes, you know, you keep dividing by 2, finally 2 will come and you divide by 2, you will get 1. So if you take 27, for example, you need to have 111 steps, and it goes up to 9,000. You see, before it scales down to 1. So look at the graph. I started with n equals 27. It goes up to 9,000, over 9,000, in fact, as you see from the graph, before 10,000, then it starts falling. So finally, the conjecture is that it will fall to 1. There are experimental evidences are there. The conjecture has been checked for very large numbers, and there is some probabilistic argument also which justifies this conjecture, but it's just an argument. This is not a proof. So this is still open, and so it's still open, and people can play this game and try to see if they can find a proof of this so-called collage conjecture. So this is my last slide, that what Gauss summarized the efforts of playing with prime numbers in his book of Disquisitiones Arithmeticae. Oh. Anyway, somebody has shared again, so I don't think I can do it anymore. So I think that was the last slide that I have, and it says that, you know, the fundamental theorem of arithmetic is such a profound statement and people should look for other proofs, and keep playing with prime numbers. Prime numbers are the basic objects, and the research on prime numbers and research in number theory goes on. And that's all that I wanted to present. Thank you so much for your patience. Excuse me.
Thank you, sir.
Yeah, I think somebody shared. So the last slide, but last slide already I spoke what is written there, that the research has to go on, and the numbers are really interesting. So that's how I end my talk. Thank you so much.
Priscilla,
Yes, ma'am.
just you end this session. You present lot of thanks.
Thank you so much, sir. We
Thank
are
you so much.
fortunate to view such an inspiring presentation about number theory from a knowledgeable and eminent person. You have produced wonderful sessions, sir. Among some hurdles, the way you explained about prime and perfect numbers is exemplary. You have spent your valuable time to ignite us. We are really grateful to you, sir. On behalf of Department of Mathematics, St. Mary's College, Autonomous, Thuthukudi, I express my hearty thanks to you. Thank you so much, sir.
Yes, thank you so much to all of you too, to really listening to me and giving me an opportunity to speak here.
Thank you, sir. Thank you. Participants, we will meet for the last session tomorrow at 6 p.m. Kindly note, we will meet tomorrow at 6 p.m. Thank you all.
Yes, ma'am. So I can leave now.
Okay, sir. Thank you, sir. Thank you.
Thank you so much. Thank you too.
Thank you, sir.
Thank you so much, ma'am.
Thank you. Leave.
இது பண்ணு வெளியே
I think